gradient of a scalar point function. If y of x comma y comma z is a scalar point function defined and differentiable at each point in a region of space, then the gradient of phi is denoted by grad phi or del phi and is defined as grad phi equal del phi equal dou phi by dou x into I bar plus dou phi by dou y into j bar plus dou phi by dou z into k bar. Directional derivative d dot d. If phi of x comma y comma z is a differentiable scalar function, then the rate of change of phi at a point p in the direction of a given vector a bar is called directional derivative of phi. It is given by del phi of p equal to a bar by modulus of a bar. The directional derivative of a scalar function phi x comma y comma z at a point p x comma y comma z in the direction of unit vector e bar is del phi dot e bar. The greatest rate of increase or maximum value of directional derivative of phi of x comma y comma z at a point p is del phi at p. If vector function f bar is said to be solenoidal vector if del dot f bar equal to 0. Irrotational vector, a vector point function f is said to be an irrotational vector if curl of f bar equal to 0 bar. Scalar potential function if for a given an irrotational vector f bar, then exists a scalar point function phi of x comma y comma z such that f bar equal to del phi, then phi of x comma y comma z is called scalar potential function of f bar. Del dot a bar cross b bar equal to b bar dot del cross a bar minus a bar dot del cross b bar. Once again I will repeat, del dot a bar cross b bar రెండు a bar cross b bar bracket లో ఉంటే equal to b bar dot del cross a bar minus a bar dot del cross b bar. Again important, del dot a bar cross b bar equal to b bar dot del cross a bar minus a bar dot del cross b bar. Okay, now del dot del cross a bar equal to 0 or divergence of curl a bar equal to 0. Curl a bar is always a solenoidal vector. Del cross of del cross a bar equal to del of del dot a bar minus del square a bar, or curl of curl a bar equal to del of del dot a bar minus del square a bar. That is equal to del dot log r bar r into r bar equal to del dot log r cross r bar plus del log r del cross r bar. Important, Green's theorem. If r is a closed region of the xy plane bounded by a simple closed curve C, and if m of x comma y, n of x comma y, dou n by dou x comma dou m by dou y are continuous functions of x and y in R, then circular integral of m dx plus n dy equal to double integral of r dou n by dou x minus dou m by dou y dx dy. Once again I repeat, if R is a closed region of the xy plane bounded by a simple closed curve C, and if m of x comma y, n of x comma y, dou n by dou x, dou m by dou y are continuous functions of x and y, or then integral of m dx plus n dy equal to double integral of dou n by dou x minus dou m by dou y dx dy, where C is traversed in positive direction. Gauss divergence theorem. If V is the volume of the region bounded by a closed surface S, and a bar x comma y comma z is a differentiable vector function over S, then surface integral of a bar dot n bar ds equal to volume integral of del dot a bar dv. Stokes theorem. If S is an open two-sided surface bounded by a simple closed curve C, and a bar x comma y comma z is a differentiable vector function, then circular integral of a bar dot d bar equal to surface integral means double integral of del cross a bar dot n bar ds, where C is traversed in the positive direction and n is outward drawn unit normal to the surface S in positive direction. Note: for every event a 0 less than or equal to p of a less than or equal to 1, p of s equal to 1. If a and b are mutual exclusive events, then p of a union b equal to p of a, or b equal to p of a plus p of b. If a1, a2 and so on n are mutual exclusive, then p of a1 union a2 union and so on an equal to p of a1 plus p of a2 and so on p of an. If phi is the empty set, p of phi equal to 0. If p of a complement is the complement of event a, then p of a complement is 1 minus p of a. If a and b are any two events, then p of a minus b equal to p of a minus p of a intersection b. Additional theorem probability. If a and b are any two events, then p of a union b equal to p of a plus p of b minus p of a intersection b. If a and b and c are three events a b c, then p of a union b union c, p of a union b union c equal to p of a plus p of b plus p of c minus P of A intersection B minus P of B intersection C minus P of C intersection A plus P of A intersection B intersection C. A finite or countably infinite probability space is said to be discrete, and uncountable probability space is said to be non-discrete. Conditional probability: let E be an arbitrary event in a sample space S where P of E greater than 0. The probability that an event A occurs once E has occurred, or in other words, conditional probability of A given A written as P of A by B is defined as follows: P of A by B equal to P of A intersection E by P of E. Let S be a finite equiprobable space with events A and E, then P of A by E equal to number of elements in A intersection E by number of elements in E, P of A intersection E by P of E. Multiplication theorem: if A and B are any two events, then P of A intersection B equal to P of A into P of B by A, that equal to P of B into P of A by B. If A and B are independent, then P of A bar B A slash B equal to P of A, P of B by A equal to P of B, P of A intersection B equal to P of A into P of B. Theorem of total probability: if B1, B2 and so on Bn be a set of exhaustive and mutual exclusive events, and A is another event associated with or caused by Bi, then P of A equals sigma I equal to 1 to n P of Bi into P of A by Bi. Bayes' theorem, the theorem of probability of causes: if B1, B2 and so on Bn be a set of exhaustive and mutually exclusive events associated with a random experiment, and A is another event associated with or caused by Bi, then P of Bi by A equal to P of Bi into P of A by Bi whole by sigma I equal to 1 to n P of Bi into P of A by Ba, where I equal to 1, 2, 3 and so on n. Suppose that to each point of a sample space we assign a number. We then have a function defined on the sample space. This function is called a random variable, or more precisely a random function. It is usually denoted by a capital letter such as x or y. A random variable which takes on a finite or countably infinite number of values is called discrete random variable. Discrete probability distribution means let x be a discrete random variable, and suppose that possible values which it can assume are given by x1, x2 and so on are arranged in increasing order of magnitude. Suppose also that these values are assumed with probabilities given by P of x equal to xi, that equal to P of xi, P of x equal to x, P of x. In general, P of x is a probability mass function. If P of x greater than or equal to 0, sigma x P of x equal to 0, where sum is taken over all possible values of x. Continuous probability distribution: if x is a continuous distribution random variable, then a function which satisfies the following requirements is called probability distribution, or probability density function of fx. F of x is greater than or equal to 0, integration of minus infinity to infinity, f of x dx equal to 1, P of a to a less than x less than b equal to P of a less than x less than or equal to b equal to P of a less than or equal to x less than b equal to P of a less than or equal to x less than or equal to b equal to integration of a to b f of x dx. Discrete random variable x ex equal to sigma equal to 1 to n xi P of xi. For a continuous random variable, e of x equal to integration of minus infinity to infinity x into f of x dx. If x is a discrete random variable having probability mass function P of x, e of g of x equal to x and sigma x g of x into P of x. If x is a continuous random variable having PDF g of x, then expectation of g of x equal to integration of minus infinity to infinity g of x into f of x dx. If c is a constant function, e of c of x equal to e of x. Expectation of x or y equal to e of x into e of y. Variance and standard deviation: variance of x equal to expectation of x minus mu whole square, x minus mu whole square, that equal to e expectation of x square minus e of x whole square. Standard deviation of x equal sigma x equal to root of variance of x. Variance of cx equal to c square variance of x. Variance of x plus or minus y equal to variance of x plus variance of y. Bernoulli trial: if in an experiment, if the probability will not change from one trial to the next, tossing a coin or dice, such trials are called Bernoulli trials. If P is the probability that an event will happen in any single Bernoulli trials called the probability of success, then Q equal to 1 minus P is the probability that the event will fail to happen, called the probability of failure. The probability that the event will happen exactly x times in n trials, that is x successes and n minus x failures will occur, is given by the probability function f of x equal to P of x equal to x equal to c of n comma x p power x q power n minus x. where the random variable x denotes the number of successes in n trials and x equal 0, 1, 2 and so on. And for binomial distribution, mean mu equal to np, variance sigma square equal to npq, standard deviation sigma equal to root over npq. Poisson's distribution, let x be a discrete random variable which can take on the values of 0, 1, 2 such that the probability of x is given by f of x equal p of x equal to x equal lambda power x e power minus lambda by x factorial, lambda power x e power minus lambda by x factorial, lambda power x e power minus lambda by x factorial, x equal 0, 1, 2 and so on, where lambda is a given positive constant called the parameter of the distribution. For Poisson distribution, mean equal to mu equal to lambda, variance equal to sigma square equal to lambda, standard deviation sigma equal to root over lambda. When n is large and p is small, then binomial distribution is very closely approximated by Poisson's distribution. We can choose lambda equal to n into p. Poisson's distribution is a limiting case of binomial distribution as n tends to infinity and p tends to 0. Continuous probability distributions, normal or Gaussian distribution. Normal distribution is another limiting form of the binomial distribution under the following conditions. The number of trials n is indefinitely large. Neither p nor q is very small. The normal probability curve density function with mean mu and standard deviation sigma is given by f of x equal to 1 by sigma root 2 pi into e power minus of x minus mu whole square x minus mu matrame square by 2 sigma square. Properties: the curve is bell shaped and symmetrical about the line x equal to mu. Mean, median, mode of the distribution coincide. As x increases numerically, f of x decreases rapidly. The maximum probability occurs at the point x equal to mu and given by p of x max equal to 1 by sigma root 2 pi. X-axis is an asymptote to the curve. Total area under the normal curve is unity. Area property: p of mu minus sigma less than x less than mu plus sigma equal 0.6826. P of mu minus 2 sigma less than mu plus 2 sigma equal 0.9544. P of mu minus 3 sigma less than x less than mu plus 3 sigma equal 0.9973. Standard normal distribution: if you let z equal to x minus mu by sigma, then the mean of z is 0 and variance is 1. The probability density function for z is f of z equal to 1 by root 2 pi e power minus z square by 2. P of a less than or equal to x less than or equal to b equal to integration of a to b f of x dx, integration of z1 to z2 f of z dz. A uniform rectangular distribution, a random variable x is said to have a continuous uniform distribution over an interval a comma b if its probability density function is constant equal to k save over the entire range of x. F of x equal to k, a less than or equal to x less than b equal to 0. Otherwise, since total probability is always unity, we have integration of a to b f of x dx equal to 1. That implies k equal to 1 by b minus a. F of x equal to 1 by b minus a for a less than x less than b 0. Otherwise, a and b, a less than b, are two parameters of the uniform distribution a comma b. The distribution is also called rectangular distribution since the curve y equal to f of x describes a rectangle over the x-axis between x equal to a and x equal to b. Mean equal to mu equal to b plus a by 2 equal to e of x. E of x square equal to integration of a to b x square f of x dx equal to b square plus a square whole by 3. Variance equal to e of x square minus e of x whole square. Sigma square equal to b minus u whole square by 12. Sigma square equal to b minus u whole square by 12. Exponential distribution, a continuous random variable x assuming non-negative values is said to have an exponential distribution with parameter theta greater than 0 if its probability density function is given by f of x equal to theta into e power minus theta x greater than or equal to 0 Otherwise, for exponential distribution, mean equal to e of x equal to 1 by theta, variance equal to sigma square equal to e of x square minus e of x equal to 1 by theta square, mean 1 by theta, variance equal to 1 by theta square. Mean, mode, standard deviation. Mean means, median means the middle value of the sample. If the sample points are arranged in ascending order, if number of elements in the sample is even, then the average of two middle values can be taken as median. Mode, the sample point occurs with highest frequency. Note mean minus mode equal to 3 of mean minus 3 median. Mean minus mode equal to 3 of mean minus median. That means mean minus mode equal to 3 mean minus 3 median. Standard deviation sigma equal to root over x bar minus x1 whole square plus x bar minus x2 whole square plus and so on x bar minus xn whole square whole by n. Next, median. The median is that value of x for which p of x less than or equal to x equal to p of x greater than or equal to x equal to 1 by 2. In the case of continuous distribution, the median corresponds to an ordinary which separates a density curve into two parts having equal areas. Mode. The mode is the value which occurs most often, or in other words has the greatest probability of occurrence at such a value of x. F of x is a maximum where f of x is probability density function. A partial differential equation is that in which there are two or more independent variables and partial differential coefficients with respect to any of the order of the differential equation is the order of the highest derivative appearing on it. The degree of a differential equation is the degree of the highest derivative occurring in it after the equation has been expressed in a form free from radicals and fraction powers as far as the derivatives are concerned. First order equations. The general form is dy by dx equal to f of xy, m dx plus n dy equal to 0, where m and n are functions of x comma y. Type 1, variable or separable. If it is possible to collect all times of x and dx on one times and y and dx and one times, then the variable is said to be separable. Then the general form of such an equation is f of y dy equal to phi of x dx equal to, that is called variable separable method. The differential equation is of the form dy by dx equal to f of xy by phi of xy, where f of xy and phi of x are homogeneous functions of the same degree in x and y. To solve a homogeneous equation, put y equal to vx, then dy by dx equal to v plus x into dv by dx. Separate the variables v and x and integrate that. Equations reducible to homogeneous form. The equation of the form dy by dx equal to x plus by plus c by a dash x plus b dash y plus z dash can be reduced to the homogeneous form as follows. When b equal to minus a dash, then the equation can be reduced to variable separable form by regrouping. When a by a dash is not equal to b by b dash, put x equal to x plus h, y equal to y plus k. Case 3, a by a dash equal to b by b dash, a by a dash equal to b by b dash equal to 1 by m, say, and then a dash equal to am. X dy minus y dx whole by x square plus y square equal to derivative of tan inverse of y by x. X dy minus y dx whole by x square minus y square equal to derivative of half of log of x plus y by x minus y. X dy minus y dx by xy equal to derivative of log of y by x. Rules for finding integrating factors. Rule 1. Integrating factor of a homogeneous equation. If m dx plus n dy equal to 0 is a homogeneous equation in x and y, then 1 by mx plus ny is an integrating factor provided mx plus ny is not equal to 0. Integrating factor for any equation of the type f1 of xy into y dx plus f2 of xy into x dx equal x dy equal to 0 if the equation m dx plus n dy equal to 0 is of the form f1 of xy into y dx plus f2 of xy into x dy equal to 0, then 1 by mx minus ny is an integrating factor provided mx minus ny is not equal to 0. In the equation m dx plus n dy equal to 0, if dou m by dou y minus dou n by dou x whole by n equal to f of x, say then e power integration of f of x dx is an integrating factor. In the equation m dx plus n dy equal to 0, if dou m by dou y minus dou n by dou x whole by n equal to f of x, say then e power integration of f of x dx is an integrating factor. In the equation m dx plus n dy equal to 0, if dou n by dou x minus dou m by dou y whole by m equal to f of y, say then e power integration of f of y dy is an integrating factor. Linear equation. A differential equation is said to be linear if the dependent variable and its differential coefficients occur only in the first degree and not multiplied together. The standard form of linear equation of the first order, commonly known as Lexibus's rule, linear equation is dy by dx plus py equal to q, where p, q are the functions of x. For the above equation, integration factor equal to e power integration of p dx, and the solution is y into integration factor equal to integration of q into integration factor dx plus c. Equations reducible to linear form. An equation of the form f dash y dy by dx plus f of y p of x equal to q of x can be reduced to a linear differential equation by substituting f of y equal to z. Higher order linear differential equations. General linear differential equation of the nth order is of the form dn power y by dx power n plus p1 dn power minus 1 by y by dx power n minus 1 plus p2 dn power n minus 2 y by dx power n minus 2 and so on, p and y equal to x, where p1 p2 and so on pn and x are functions of x. Are only linear differential equations with constant coefficients are of the form dn power 1 y by dx power n plus k1 dn power minus 1 by dx power n minus 1 plus k2 dn power n minus 2 by dx power n minus 2 and so on, k and y equal to x, where k1 k2 kn are constants and x is a function of x. Denoting d by dx, d square by dx square, dq by dx cube, etc. by d square, d cube, etc. so that dy by dx equal dy, d square y by dx square equal d square y, d cube y by dx cube, d cube y, etc. The equation above can be written in the symbolic form d power n plus k1 d power n minus 1 and so on, kn into y equal to x, f of d into y equal to x, where f of d equal to d power n plus k1 d power n minus 1 and so on, plus k1 is a polynomial in D. The symbol D stands for the operation of differentiation and can be treated much the same as algebraic quantity. In a particular, if f of x equal to 0 is in equation 1, then it is called homogeneous linear differential equation. Otherwise, that is x is not equal to 0, then equation 1 is called non-homogeneous linear differential equation in a higher order. Working procedure to solve equation 1. Write the equation 1 in the form of f of t into y equal to x. The auxiliary equation now is f of m equal to 0. Let m1, m2 and so on m1 be the roots of auxiliary equation. Finding complementary function. The solution of equation when x equal to 0 is called complementary function. We can write the complementary function using the rules given below. The characteristic roots are real and distinct, say m1, m2 and so on m3. Characteristic function yc equals c1 into e power m1x plus c2 into e power m2x plus c3 into e power m3x and so on. The characteristic roots are real and two roots are equal, say m1, m2, say m1, m1, m3. Then say characteristic function yc equal to c1 plus c2x into e power m1x plus c3 into e power m3x. The characteristic roots are real and three roots are equal, m1, 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 m4. yc equals c1 plus c2x plus c3x square into e power m1x plus c4 e power m4x. A pair of roots are complex, say alpha plus I beta, alpha minus I beta, m3. y is equal to e power alpha x, c1 cos beta x plus c2 sin beta x plus c3 e power m3x. Two pairs of roots are complex, say alpha plus r minus I beta, alpha plus r minus I beta, m5. Then e power alpha x, c1 plus c2x into cos beta x plus c3 plus c4x into sin beta x plus c5 into e power m5x. A pair of roots are irrotational, say alpha plus root beta, alpha minus root beta, m3. cf equal to yc e power alpha x into c1 of cos h into root beta x plus c2 of sin h into root beta x plus c3 into e power m3x. Two pairs of roots are irrotational, say alpha plus or minus root beta, alpha plus or minus root beta, m5. cf equal to yc e power alpha x into c1 plus c2x into cos h of root beta x plus c3 plus c4x into sin h of root beta x plus c5 into e power m5x. Finding particular integral pi form equation. Particular integral equal yp equal to 1 by f of d into x. By following some rules, we can write yp. Write the complete solution cs. The complete solution is cf plus pi yc plus yp. The solution of a homogeneous linear differential equation of higher order in the form f of d equal to y is given by y equal to yc itself. Rule for finding particular integral. Rule 1. X equal to e power ax. yp equal to 1 by f of d into e power ax. 1 by f of a into e power ax. If f of a is not equal to 0, if f of a equal to 0, yp equal to x of e power ax by f dash of a. If f dash of a is not equal to 0, if f dash of a equal to 0, yp equal to x square into e power ax double dash of a. If f double dash of a is not equal to 0 and so on. E power ax by d minus a whole power n equal to x power n into e power ax by n factorial. When x equal to sin of ax plus b, yp equal to 1 by f of d into sin of ax plus b. To evaluate p integral, particular integral, we have to replace d square with e minus a square in f of d provided denominator is not 0. If the denominator is 0, then yp equal to x into 1 by f dash of d in sin of ax plus b. If the denominator replaces d square with minus a square in f dash of d, if denominator is not 0 and so on. Rule 3. When x equal to x power m being a positive integer, yp equal to 1 by f of d x power m, f of d whole inverse into x power m. To evaluate, expand f d inverse in ascending order of d by binomial theorem as far as dm for m and operate on x power m by term. When x equal to e power ax into v, where v is a function of x, yp equal to 1 by f of d into e power ax into v, that equal to e power ax into v by f of d plus a. When capital X equals small x into v, then yp equal to 1 by f of d into v xv. X of 1 by f of d into v minus f dash of d by f dash of d is d square into v. When x is a new function of x, yp equal to 1 by f of d into x. Resolve 1 by f of d into partial fractions and operate each partial fraction on x by using 1 by d minus ax equal to e power ax integration of x into e power minus ax dx. Euler-Cauchy's homogeneous linear equations. An equation of the form x power n d power n y by dx power n plus k1 x power n minus 1 d power n minus 1 by dx power n minus 1 and so on. Kn minus 1 x of dy by dx plus kn y equal to x, where x is a function of x, is called Euler-Cauchy's homogeneous linear equation. Such equations can be reduced to linear differential equations with constant coefficients by putting x equal to e power z or z equal to log x and d equal to d by dz. Then x of dy by dx equal to dy, x square of d square by dx square equal to d of d into d minus 1 into y. Similarly, x cube of d cube y dx cube d into d minus 1 and d minus 2 into y and so on. Conjugate of a complex theory. Z equal to x plus y, x minus iy. Modulus means root of x square plus y square. Geometrical representation of complex numbers. Properties of moduli and amplitude of complex numbers. Modulus z is a non-negative real number. Modulus of z1, z2, z3 is equal to z1, modulus of z1, modulus of z2 and so on. Modulus of z1 plus z2 is less than equal to modulus of z1 plus z2. Modulus of z1 minus z2 is less than equal to modulus of z1 plus modulus of z2. Sin iz, I sin hx, hz, cos iz, cos hz, tan iz, I tan hz, cos hiz, cos z, sin hiz, I sin z, tan hiz, I tan z, tan z equals sin 2x plus I sin h 2y whole by cos 2x plus cos h 2y. If your complex function f of z is differentiable at point z0 and also differentiable at every point in some neighborhood of a point z0, then the function f of z is called an analytic function at a point z equals z0. A complex valid function f of z is said to be analytical in a region R if f of z is analytical every point of the region R. Analytical function is also known as regular or holomorphic or monogenic function. Singularity, a point at which the function f of z fails to be analytic is called a singular point or singularity of f of z. Entire function, if a function f of z is analytical at every point in the whole finite complex plane, Argand plane, then the function f of z is an entire function. Cauchy-Riemann equations, a necessary condition that when w equal to f of z equal to u of xy plus I into e of xy to be analytic in region R, in that in R, u and v satisfy the Cauchy-Riemann equation dou u by dou x equal to dou u by dou y and dou u by dou y equal to minus dou v by dou x. If the partial derivatives in equation 1 are continuous in R, then the Cauchy-Riemann equation are sufficient conditions that f of z be analytic in R. The function f of z equal to u of xy plus I into e of xy is analytical if f dash of z equal to dou u by dou x plus I into dou u by dou y. F dash of z equal to dou u by dou x minus I into dou u by dou y. F dash of z equal to dou u by dou y plus I into dou u by dou x. Harmonic function, the equation f of x fxx plus fyy equal to 0 and del square f equal to 0, where f is a function of x and y is called a Laplace equation and the function f of xy is called a harmonic function. Cauchy's integral theorem, if f of z is analytic and f dash z is continuous at every point within and on simple closed curve C, the integration of f of z dz equal to 0. Cauchy's integral theorem for multiply connected region, if f of z is analytical at every point within a triply connected region or bounded by three simple closed curves C1, C2, C3 but not analytical within C1 and C2 and C3, then integration of f of z dz equal to integration of C1 f of z dz plus circle integral of f of C2 f of z dz. Cauchy's integral formula. Cauchy's integral form f of z is of the form f of z equal phi of z by z minus z naught, where phi of z is analytical at every point within a non-simple closed curve C and z naught is any point within C. Then circle integral of f of z dz equal to circle integral of phi of z by z minus z naught dz equal to 2 pi I in phi of z naught. Cauchy's integral formula for the derivative of an analytical function, if f of z is of the form f of z equal phi of z by z minus z naught whole power n plus 1, where phi of z is analytic at every point within n on a simple closed curve C and z naught is any point within C, then circle integral of f of z dz equal to circle integral of phi of z z minus z naught whole power n plus 1 dz equal to 2 pi I by n factorial into phi power n z of z naught, where phi power n of z naught is the nth derivative of phi of z at z equals z naught. The Cauchy's integral formula expresses the value of an analytic function at an interior point of region R in terms of its value on the boundary of the region. Taylor's and Lorentz series, complex power series, an infinite series of the form a0 plus a1 z minus z0 plus a2 z minus z0 whole square plus and so on a n z minus z0 whole power n plus and so on, or sigma n equals 0 to infinity a n z minus z0 whole power n is called a power series about the point z equals z0 or in positive direction power of z minus z0. In the above series, a0, a1, a2 and so on, an are real or complex constants which are called coefficients of power series. Z0 is a fixed complex constant which is called center of the power series and z is the complex variable. Taylor series, if f of z is analytical at every point within a circle C having center at z0, then for every point z Inside C, the function of z can be expressed as a power series in positive powers of z minus z naught or about a point z minus equal z naught. Then f of z equal to f of z naught plus z minus z naught into f dash of z naught plus z minus z naught whole square by 2 factorial f double dash of z naught and so on. That equals sigma n equals 0 to infinity a n z minus z naught whole power n, where a n equal to 1 by 2 pi I in circular integral of f of t by t minus z naught whole power n plus 1 into dt. That equal nth derivative f of z naught nth derivative whole by n factorial. The RH of 1 is called Taylor series expansion of f of z about z equals z naught, and its ROC is given by modulus of z minus z naught less than r, where the radius of convergence r is the distance from the center of the power series z naught to its nearest singular point of f of z. Lorentz theorem: if f of z is analytical at every point within a ring shaped region or bounded by two concentric circles C1 and C2 with center at z0 and respect to radii r1 and r2, r1 greater than r2, then for every point z within R, the function f of z can be expressed as a power series in both positive and negative powers of z minus z0 or about a point z equals z0. Let f of z equals sigma n equals 0 to infinity a n z minus z0 whole power n plus sigma n equal to 1 to infinity b n z minus z0 power minus n, where a n equal to 1 by 2 pi I circular integral of c1 f of z dt by f of t dt by t minus z0 whole power n plus 1 n equal 0 1 2 and so on. b n equal 1 by 2 pi integral of c2 f of t dt by t minus z0 whole power minus n plus 1 n equal 1 2 3 7. That's all. Taylor series expansion of f of z about original z equal is called Maclaurin series of z equal to f of 0 plus z into f dash of 0 plus z square by 2 factorial f double dash of 0 plus and so on is the required Maclaurin series. Types of singular points. Isolated singular point: if z equal to z0 is a singularity of f of z and f of z is analytical at every point in at least one neighborhood of a point z equal z0, then z equal z0 is said to be isolated singularity of f of z. If f of z equals z plus 1 by z and z minus 4, here z equals 0 and z equals 4 are isolated singularities since there exists no other singularity around the points z equals 0 and z equals 4. Types of singular points: if z equals z0 is an isolated singular point of f of z, then f of z equals sigma n equals 0 to infinity a n of z minus z0 whole power n plus sigma n equal to 1 to infinity b n of z minus z0 whole power minus n, where sigma n equal to 0 to infinity a n of z minus z0 whole power n is called analytic part, and sigma n equal to 1 to infinity b n of z minus z0 whole power minus n is called principal part of Lorentz series. Removable singularity: if the principal part does not exist in the Lorentz series expansion of f of z about z equals z0, then singularity point z equals z0 is called a removable singularity of f of z. Pole of order m: if the principal part of Lorentz series contains a finite number of terms, say m terms, then the singular point z equals z0 is called a pole of order m of f of z. Essential singularity: in the Lorentz series expansion of f of z and about z equals z0, if the principal part contains infinite number of terms, then the singular point z equals z0 is called an essential singularity of f of z. Isolated essential singularity: the limit point of zeros of f of z is an isolated essential singularity. Non-isolated essential singularity: the limit point of poles of is in non-isolated. Cauchy's residues theorem: residue of f of z. If z0 is an isolated singularity point of f of z, then the coefficient of 1 by z minus z0 or z minus z0 whole inverse in the Lorentz series expansion of f of z about the point z0 is called residue of f of z at z0, and it is denoted by residue of z equals z0 of f of z, or residue of f of z equals z0 equal to the residue of f of z equals z0, the coefficient of 1 by z minus z0, that equal to b1 equal to 1 by 2 pi a integral of c f of z dz, where c is the circle modulus of z minus z0 equal to r, such that f of z is a analytic in 0 less than modulus of z minus z0 less than r. Evolution of residues at singularities. Residue at a removable singular point: if z equals z0 is a removable singular point of f of z, then residue of f of z equals z0 equals 0 equal to b1, since there is no term in the principal part of the Lorentz series expansion of z about z0. Residue at poles: if f of z equal to p of z by q of z, where p of z q of z are polynomials has a simple pole at z equals z0, then residue of f of z equals z0 equal limit z tends to 0 z minus z0 into f of z. If f of z equal phi of z by psi of z has a simple pole at z equals z0, where phi of z0 is not equal to 0, psi of z0 equals 0, then psi dash of z0 is not equal to 0, then residue of f of z psi of z0 by psi dash of z0. If f of z equals psi of z by z minus z0 has a simple pole at z equals z0, where phi of z0 is not equal to 0, then residue of f of z equals z0 equal phi of z0. If f of z has a pole of order m at z equals z0, then residue of f of z at z equals z0 equal to 1 minus m minus 1 factorial into limit z tends to z0 d power m minus 1 by z dz power m minus 1 z minus z0 whole power m f of z. Residue at an isolated essential singular point. If z equals z0 is an isolated essential singular point of f of z, then expand f of z at Lorentz series about z equals z and collect the coefficient of f1 by z minus z0 in the Lorentz series, which gives the residue of f of z. Residue of f of z equals z0 equal to b1. Cauchy's residues theorem. If f of z is an analytical at every point within and on a simple closed curve C, except at a finite number of isolated singular points z1, z2, z3 and so on within C, then circle integral of f of z dz equal to 2 pi I into sigma j equal to 1 to n rj, where rj equal to residue of f of z, z equal to zj. Numerical methods. Bisection method. Consider the equation f of x equals 0. Using trial and error, we have to find two numbers a and b such that f of a and f of b are of opposite signs. As an approximation to the real root, x1 equal to a plus b by 2. If f of x1 less than 0, then the root of the equation lies in x1 comma b. In this case, choose x2 equal to x1 plus b by 2. If f of x1 equals 0, then x1 is the root of the equation. The problem is solved. If f of x1 greater than 0, then the root lies in a1 x1. Choose x2 equal to a1 plus x1 by 2. Similarly, we compute x3, x4 and so on. To continue until the required accuracy, the absolute difference between two consecutive values is less than a pre-assigned number epsilon. Bisection method is the simplest iterative method and convergence to the root is guaranteed. The bisection method is considered as a slow and steady. Rate of convergence is only 1 bit per iteration. The bisection method cannot be applied to find the complex roots of an equation. Newton's-Raphson method. Consider the equation f of x equals 0. Let x naught be the initial approximation to the root. Let x1 equal to x naught plus h. Substituting in 1, we have f of x naught plus h equals 0, expanding by Taylor series and neglecting h square, h cube, etc. f of x naught plus h into f dash of x naught equals 0, h equal to minus of f of x naught by f dash of x naught. Substituting t, we get x1 equal to x naught minus f of x naught by f dash of x naught. x1 equal to x naught minus f of x by f of x naught by f dash of x naught, which is first approximation to the root. Similarly, x2 equal to x1 minus f of x1 f dash of x1. x3 equal to x2 minus f of x2 by f dash of x2. xn plus 1 equal to xn minus f of xn by f dash of xn. Geometrically, the method consists in replacing the part of the curve between the point x0, f of x0 and x-axis by means of a tangent to the curve at the point. The point where the tangent intersect x-axis is taken as a first approximation to the root. The method is instituted to the initial guess x0. If x0 is not sufficiently close to the root, then convergence on the root is not guaranteed. Newton-Raphson method has a quadratic convergence. The order of convergence equal to 2. The error at each iteration is proportional to the square of the error at previous iteration. Newton-Raphson method converges more rapidly than other methods. Since two functions evaluations are required for each iteration, Newton-Raphson method requires more computing time. The method can be used for solving algebraic and transcendental equations, and it can also be used if the roots are complex. Newton-Raphson method is useful in cases of large values of f dash of x, that is when the graph of the function y equal to f of x while crossing x-axis is nearly vertical. Newton-Raphson method has quadratic convergence provided f dash of x and f double dash x are not 0. Newton-Raphson method is generally used to improve the result obtained by other methods. Method of false position or regula falsi. This is another method for finding the real root of a non-linear equation of x equals 0. We choose 2 points a and b such that f of a and f of b are of opposite signs. Hence, a root must be lying between these points. Now, the equation of the chord joining the 2 points a, f of a and b, f of b is given by y minus f of a by x minus a equal to f of b minus f of a by b minus a. The method consisting in replacing of the part of the curve between the points. Just stop. xn plus 1 equal to xn minus f of xn whole the bracket xn minus xn minus 1 by f of xn minus f of xn minus 1. Xn separate minus f of xn into xn minus 1 by f of xn and f of xn minus 1. Instead of choosing two values of x such that the function has opposite signs at these values, we choose two values nearest to the root for each iteration. This method is applicable only if one is sure that there is a root in the vicinity of x1, the starting value. In this method, we approximate the graph of the function y equal to f of x in the neighborhood of the root by a straight line secant passing through the points xi minus 1 fi minus 1 and xi fi. The order of convergence is 1.62, converges faster than false position method. No guarantee of convergence if not near root. The method fails if f of xi equal to f of xi minus 1. It may be considered the most economical method, giving reasonably rapid convergence at a low cost. The amount of computation effort is one functional evaluation. On the average, secant method is superior to Newton-Raphson method. Euler's method. Consider dy by dx equal to f of xy with initial conditions y of x naught equal to y naught. We want to find out the value of y at xl equal to 1. Divide x naught comma l into n equal parts of width h. Let x1 and x2 and so on xn minus 1 xn equal to l to be the intermediate points. Now in y1 equal to y naught plus h into f of x naught y naught, y2 equal to y1 plus h of x1 h into f of x1 y1, yn equal to yn minus 1 plus h into f of xn minus 1 yn minus 1. The method is stable if 1 plus dou f by dou y less than 1 modulus. Then the errors will be damped down with successive iterations, otherwise the error increase in successive iteration. The procedure will be unstable. It is based on the linear term in the Taylor's expansion of f of xy. In practice, the error build up in the using the method is substantial. Method is rarely used. This method is also called as Runge-Kutta first order method. This method is also called as Runge-Kutta first order method. Next, Huon's method, modified Euler's method, or Runge-Kutta second order method. Consider dy by dx equal to f of xy with initial conditions y of x naught equal to y naught. Initially, y1 is compared by Euler's method, y1 of p equal to y naught of plus h into f of x naught y naught, where p indicator predictor. Then modified value of y1 is given by y1 equal to y naught plus h by 2 f of x naught y naught plus f of x1 y1. Similarly, we can find y2 y3. This method is also called as modified Euler's method or second order Runge-Kutta method. Runge-Kutta method, that to solve dy by dx equal to f of x with the coordination y of x naught equal to y naught, let h denote the interval between equidistant values of x. If the initial values are x naught y naught, then the first increment in y is computed from the formula given by k1 equal to h into f of x naught y naught, k2 equal to h into f of x naught plus h by 2 y naught plus k1 by 2, k3 equal to h into f of x naught plus h by 2 y naught plus k2 by 2, k4 equal to h into f of x naught plus h y naught plus k3, delta y equal to 1 by 6 1 whole by 6 into k1 plus 2 k2 plus 2 k3 plus k4 y1 equal to y naught plus delta y. The process of finding or evaluating a definite integral I equal to integration u to b f of x dx from a set of numerical values of the integrand f of x. The process of numerical integration is solved by first approximating the integrand by a polynomial with the help of an interpolation formula, and then integration this expression between the desired limits. Consider I equal to integration of u to b f of x dx. Let y equal to f of x be given for certain equidistant values of arguments, say x naught plus h, x naught plus 2h. Let the range b minus a be divided into n equal parts, each of which of width h. B minus a equal to nh. Let x naught equal to a, x1 equal to a plus h, x2 equal to a plus 2h. Compute x y equal to f of x, s naught y naught, x1 y1 x2 y2. Trapezoidal rule, I equal to h by 2 whole bracket y naught plus yn plus 2 into y1 plus y2 plus and so on yn minus 1. Here we have taken y a polynomial first degree in x or straight line. There, due to trapezoidal rule is given by it is less than or equal to m2 b minus a whole cube by 12 n square equal to m2 n h cube by 12, where m2 equal to maximum value of f double of h of x modulus in the interval a comma b. If as h is numerically smaller than 1, the dominant term is the h cube term. The rule gives exact value at the integral if f of x is polynomial function of degree 0 or 1. If the interval at which f of x is tabulated is half, the error would be reduced by 8th Simpson's rule. A popular numerical integration technique method, I equal to integration of 0 to a to b f of x dx. Divide a comma b into n equal parts where n is even number. The method is based on approximating the function of x by fitting quadratic through sets of 3 points. I equal to h by 3 into y naught plus yn plus 4 into h by 3 full bracket y naught plus yn plus 4 into y1 plus y3 plus and so on yn minus 1 plus 2 into y2 plus y4 and so on yn minus 2. Error term due to Simpson's rule is es less than or equal to m4 b minus a whole power 5 by 180 power n power 4. If f of x is a polynomial degree less than or equal to, then the Simpson's rule gives exact value of the integral. If the tabulated interval is half, the error is reduced by a factor of 32.